Next problem, find the Fourier transform of capital F of x. So instead of small f of x, they have given capital F of x, right? Don't get confused, right? Use capital F of x instead of small f of x. Actually, as per our notation, if we are using capital F, that is Fourier transform of particular function. But in this particular case, in this problem, they have given, instead of small f, they have given capital F. So we are considering capital F of x is a function. And for Fourier transform, you can use the script f. That is what, to avoid the confusion, right? So f of x is defined by 1 if mod x less than a, 0 if mod x is greater than a. And hence evaluate, first evaluation integral minus infinite to plus infinite sin pa cos px by p dp, and second evaluation integral minus infinite to plus infinite sin p by p dp. So we know that Fourier transform of capital F of x, which is equal to Fourier transform of f of x, which is equal to f bar of p, which is equal to 1 by root 2 pi integral minus infinite to plus infinite e power I px f of x dx. So given f of x is equal to 1 if x mod x is less than a, 0 if mod x is greater than a. Mod x is less than a means x lies between minus a to plus a. Mod x is greater than a means otherwise. So other inequalities, right? So x is greater than minus a, and x is less than minus a, and x is greater than capital S a, right? In both cases, the value of f of x is 0. So 1 if minus x lies between minus a to plus a, 0 otherwise. That is equation number 1. Now Fourier transform of f of x is equal to 1 by root 2 pi integral minus infinite to plus infinite e power I px f of x dx. Therefore, that is nothing but f bar of p, Fourier transform of capital F of x, which is equal to 1 by root 2 pi. Now capital F of x, that is given f of x is in the interval. In the interval, when x lies between minus a to plus a, its value is 1. Then all other intervals, it takes the value 0. So that is why we are going to split the integration, because the integration is over minus infinite to plus infinite. So we are taking first interval minus infinite to minus a, first interval e power I px f of x dx, plus second interval minus a to plus a e power I px f of x dx, and third interval a to infinite e power I px f of x dx. Now we are going to substitute the value of f of x in the particular intervals. In the first interval minus infinite to minus a, f of x value 0. Then the second interval minus a to plus a, in that interval f of x value 1. Then last interval a to infinite, f of x value again 0. We are substituting that value. So 1 by root 2 pi. So e power I px 0 into dx plus integral minus a to plus a e power I px into 1 dx plus integral a to infinite e power I px 0 into dx, which is equal to 1 by root 2 pi. So first and third integral become 0, because 0 into something 0. So middle one, integral minus a to plus a e power I px into 1 e power I px dx. So we are going to evaluate the integration e power I px. We know e power ax, integral e power ax is equal to e power ax by a. Instead of a, you are having ip. So 1 by root 2 pi e power I px by ip, lower limit minus a, upper limit plus a, because we know integral e power ax dx is equal to e power ax by a. So using the upper limit, 1 by root 2 pi e power I p a by ip minus e power lower limit minus ipa by ip. So here 1 by root 2 pi ip is common, LCM. So 1 by ip e power ipa minus e power minus ipa. So that is equal to 1 by p root 2 pi into e power ipa minus e power ipa divided by 2i. we are dividing by 2 and multiplying by 2, right? So that is equal to 2 divided by p root 2 pi sin pa, because e power I ax minus e power minus I ax by 2i, which is equal to sin ax. We are using that formula, right? That is equal to, therefore the Fourier transform of f of x, which is equal to f bar of p, which is equal to 2 and root 2. 2 in the numerator, denominator root 2 get cancelled, so you will get root 2 in the numerator. The denominator already you are having root pi, so root of 2 divided by pi into 1 by p sin pa, when p not equal to 0. Suppose p equal to 0, so you will get from 1 and 2 f bar of p, which is equal to 1 by root 2 pi. So integration minus infinite to plus integral minus infinite to minus a e power, instead of p you put 0, 0x, f of x is also 0 in this interval, into dx, plus 1 by root 2 pi minus a to plus a e power I 0x into 1 into dx, plus 1 by root 2 pi integral a to infinity e power I 0x into 0 dx. So you will get 1 by root 2 pi integral minus a to plus a e power I 0x e power 0 1 1 into 1 1 1 into dx, you will get dx. So integral dx we know x, so lower limit minus a, upper limit a. Substituting upper and lower limit, 1 by root 2 pi a minus a, that is equal to 1 by root 2 pi 2a. 2 and root 2 get cancelled, so you will get root of 2 divided by pi into a. So therefore Fourier transform of f of x, which is equal to root of 2 divided by pi into a when p equal to 0. So we know the inversion formula from the inversion theorem. F bar of p, if f bar of p, which is equal to 1 by root 2 pi integral minus infinite to plus infinite e power I px f of x dx, then f of x, which is equal to 1 by root 2 pi integral minus infinite to plus infinite e power minus I px f bar of p dp, right? This is inverse Fourier transform of f bar of p, right? Fourier transform of f of x, right? So using 3, f of x is equal to 1 by root 2 pi integral minus infinite to plus infinite e power minus I px, using f bar of p from 3 root 2 divided by pi 1 by p sin pa. We are using the case p not equal to 0, right? 1 by root 2 pi integral root 2 by pi integral minus infinite to plus infinite cos px minus I sin px into 1 by p sin pa dp, right? We know Euler's formula, e power minus ix, which is equal to cos x minus I sin x. So here e power minus I px, so cos px minus I sin px. So therefore f of x is equal to 1 by pi, root 2 get cancelled, root pi into root pi in the denominator becomes pi, 1 by pi integral minus infinite to plus infinite, so cos px into sin pa, we are splitting into 2 integration, by p into dp, the second one minus I into 1 by pi integral minus infinite to plus infinite sin px into sin pa divided by p into dp. That is equation number 4. Since sin is always odd function, cos is always even function, right? So sin pa is an odd function, sin px is an odd function. So sin px into sin pa, odd multiplication of odd function to odd function becomes an even function, right? Sin pa into sin px, so is an even function. We know 1 by p is always odd function, p 1 by p all are odd function, so 1 by p is odd function. Sin pa into sin px is an even function, multiplication of two odd function becomes an even function into an odd function 1 by p. So sin pa sin px even function into 1 by p is an odd function, multiplication of even function into odd function, you will get odd function. Therefore sin pa sin px by p is an odd function. Hence from the properties of definite integral minus infinite to plus infinite odd function, which is equal to 0, that is sin pa sin px by p into dp, which is equal to 0. So 4 becomes f of x, which is equal to 1 by pi integral minus infinite to plus infinite sin pa cos px by p dp. So using 1 1 by pi integral minus infinite to plus infinite sin pa cos px by p into dp, which is equal to f of x from 1, value of f of x is 1 modulus x less than a, 0 modulus x is greater than a. This implies 1 by pi integral minus infinite to plus infinite sin pa cos px by p dp, which is equal to 1 modulus x is less than a, 0 modulus x is greater than a. Multiply both side by pi. So pi into pi on the left hand side become 1. So you will get minus infinite to plus infinite, integral minus infinite to plus infinite sin pa cos px by p into dp, right? That is left hand side. So in the right hand side, pi into 1 pi, pi into 0 0. So it is equal to pi modulus x less than a, 0 modulus x greater than a. That is equation number 5. Put x is equal to 0 and a is equal to 1 in 5. So you will get integral minus infinite to plus infinite sin p into 1 cos p into 0 by p dp. That is, it is equal to pi, right? Because a is 1, x is 0. So x modulus x is always less than 0 is less than 1. So we are using the first one. So the value is pi, right? That is why we are taking pi. Since sin p is an odd function, 1 by p is an odd function. Therefore sin p by p is an even function. Odd function, product of two odd function, you will get even function. Hence, from the properties of definite integral, integral minus infinite to plus infinite sin p by p dp, which is equal to, so for even function property is 2 to 0 to infinite integral, right? Integral 0 to infinite sin p by p dp, right? So 6 implies, that is the sixth equation is integral minus infinite to plus infinite sin p into 1 sin p cos p into 0 cos 0 is 1. So you in the numerator you will get sin p by p into dp equal to pi, right? Yeah, we are using that one. So instead of integral minus infinite to plus infinite, we are using 2 times 0 to infinite integral 0 to infinite sin p by p dp, which is equal to pi. Therefore integral 0 to infinite sin p by p dp is equal to pi by 2, which is to be proved, right? The two cases evaluation has finished. Minus infinite to plus infinite sin pa cos px by p dp, that is equation number 5. And the last one, integral 0 to infinite sin p by p dp equal to pi by 2. If you want minus infinite to plus infinite, that is equal to pi, right? That's all. Thanks.